All right. I want to talk a little bit about the variational principle, Hartree-Fock theory, and the meaning of orbitals, or at least how you get them. I'm going to do my best to make this a little shorter than the last ones. We'll see whether I can do that and whether it's sufficient for you folks. All right, the variational principle. There's a lot of math on that slide, but let me say three things. If you use the exact non-relativistic Hamiltonian, so we can talk about what relativity does to this, but let's assume that we're working on lighter atoms, say the top five, maybe five at least rows of the periodic table. And you use a wave function that's normalized, and it's easy enough to fix it up if it's not normalized. Then when you take what's called the expectation value of the Hamiltonian with this guessed wave function you have. So this is a wave function, you don't know if it's right, you don't know if it's exact, it's probably not, but you take the expectation value. So that is psi star h psi integrated over all space. Then you get an energy, and you get an energy just as you would any other sort of value here. It just happens to use the Hamiltonian, that's the energy. And what the variational principle says under the two conditions above is that energy has to be above the ground state energy, the exact ground state energy. So that means that you can judge how good or how relatively good a pair of wave functions are when it comes to the energy just by comparing their energy. Since both of them have to be above the exact ground state energy, the one that is lower is necessarily closer to the ground state energy. And it's quite remarkable. It could have been otherwise. It could have been that and there are lots of methods that we have that do provide energies that are both above and below the exact ground state energy, perturbation theory being one of them. But if you use an expectation value to calculate the energy, then by golly, you know, and you use the right Hamiltonian, then you know that your energy is above that of the ground state. And that becomes a prescription for how to optimize, to find the best wave function of a form that you are using. So you saw in your reading, or you will see in your reading, that the simplest kind of wave function that we might use is a so-called Hartree-Fock wave function. We write it as electrons in orbitals. So here across that top row, you see electron 1 being placed in orbital 1, 2, 3, 4, up to n. And these are so-called spin orbitals. They have a part that describes the probability amplitude for the electron in space. And then you have another piece that multiplies multiplies the spatial part that determines the spin, alpha or beta. And you can see the way this is set up, each row represents a different electron, each column represents a different orbital. And we write it symbolically in this way, and because there are n factorial terms, this 1 over square root of n factorial makes sure it's normalized if each of the individual spin orbitals are normalized. But the beauty of this form is it is manifestly antisymmetric under particle interchange. And we need that for fermion wave functions. Particle interchange would be like switching electrons labels 1 and 2. That would be like putting this row up here and the top row in the second row. That's switching two rows, and the determinant has the same absolute value under those conditions. It just has its change sign. So that automatically satisfies Fermi statistics, which we need for electrons. Okay, so then you could go ahead and evaluate the energy of that wave function. And it's pretty darn simple. It reduces to a sum over one electron terms. This is kinetic energy plus attraction of each electron, the electron to the nucleus, plus the nuclear repulsion terms. So there's 1 for each electron here. And these are what we call the electron repulsion integrals. So in another video, I'll talk a little bit more in detail about these. For the moment, let's just say that this term represents what we would think classically, the repulsion of an electron in orbital I, so its absolute value squared, with that in an orbital J. So 2 electrons repel one another, and the repulsion goes as 1 over the distance between them. This term is a little harder to understand. This is electron 1 in I and J, electron 2 in J and I, and this comes about due to that anti-symmetry, the fact that we have used a Slater-determinant wave function. But if you said, look, I know that this is above the ground state energy, no matter what orbitals I pick, I and j, running from 1 to n, then why don't I just minimize the energy with respect to the shapes of those orbitals? You get a set of equations that look like this. They're little tiny Schrodinger equations. You get an operator on spin orbital I equals an orbital energy times spin orbital I. So it's a little eigenfunction equation. And you see what's interesting about it is it's got a kinetic energy, it's got an attraction to the nucleus, and it's got the so-called Hartree-Fock potential here. And that really has to do with these electron repulsion terms. The J and K integrals, I write them out here. We'll talk more about them now, but you can see that this is, look, if this is a wave function, which is an amplitude that can be plus or minus, the absolute value squared is a charge density. It's always positive or 0. Here's another charge density, and I am just picking a distance 1 and a distance 2, or position 1 and position 2. I calculate the distance between those and multiply it by a little volume element and a spin function for each. And then I add them up by integrating. But here's that weird thing, that K, which is orbital I, orbital J for electron 1, orbital J, orbital I for electron 2. And again, in the next video, we'll talk a little bit more about that. But for Hartree-Fock, the key is that each of the orbitals satisfies a 1-electron Schrodinger-like equation, but it's just for 1 electron. V Hartree-Fock is defined, and you see it in the text, in terms of electron repulsions, and that's all it's got. J and K are those repulsions. We call them Coulomb for a classical interaction, and K an exchange for this non-classical quantum mechanical effect. And just as a teaser, I'll say that in the next video, I'll talk a lot more about those Coulomb and exchange integrals and how they affect the energy.